Welcome to today's colloquium. We are happy to have Jun Ye from Jilla here, Jilla in Boulder, Colorado. Jun is very well known in the community for building, I would say, the greatest, most precise clocks. It's really amazing, and he will show us what you can all do with these clocks. But first, let me say a few words about Jun. Jun is a member of the National Academy of Sciences, also a member of an APS fellow, an OSA fellow. He won a number of prizes, so this page is nearly filled with prizes. The most recent one is the Herbert Walter Award, a Breakthrough Prize, the MICUS Quantum Prize, a Norman Ramsey Prize, a Rabi Prize, and so on. So a really distinguished speaker, and I want to say that I value Jun more for his experimental work. His lab does really fantastic, groundbreaking work using ultra-cold atoms in optical lattices. Jun has also worked on studying ultra-cold quantum chemistry, but most recently he focuses on clocks and pushed really the art of measuring time into a new regime where you can actually tell the difference whether you're 1 millimeter higher or lower by just looking at how fast the clock ticks. Yeah, let's welcome Jun for his talk on a clock for quantum and fundamental physics.
Well, thank you very much, Atma, for the wonderful, kind introduction. And it's always, I think this is my maybe 4th or 5th trip to Berkeley, and always felt personally connected to this community because I learned a lot from the pioneers sitting in this audience, actually. And some of them are no longer sitting in here. And I remember came here and Charlie Tongs was sitting in the front. And a very humbling experience. And also, my group have benefited tremendously over the years of taking on students from this area. Dan's PhD students, Hartmut's undergraduate students, and they play major roles in our research progress. And I will have a page, which is a Berkeley page. Those were like experiments done by the students from Berkeley. And if you would like to come to my lab, you know, be most welcome. Every Berkeley student would be most welcome. I personally also felt was very, tell you a very quick personal story. I was 2 years into my faculty position in Jilla, and the first time outside university came to approach me saying, Jun, are you interested in moving? Was actually from UC Berkeley. And Roger Falconi and Ron and so on. And very early on, 2001, I feel really flattered. I haven't done anything, and yet people were like, you know, are you interested in coming to the Bay Area? And so thank you. And hopefully in the next 15 minutes, I'll share with you some of the interesting aspect of the clock making process. And as you can see, you know, building a clock is much, much more than building a timepiece. It's really actually a fantastic opportunity to look for quantum science frontiers and fundamental physics. We have a quantum center here, right? Dan is actually 2 quantum centers. There's a QSA quantum center. There's a NSF-founded quantum center. Dan Stepper-Kern is a director. And one area, of course, that we are emphasizing quantum information science, pushing for building quantum computers and quantum sensing, quantum networking. Lots of work is going on campus and on Lawrence Berkeley National Labs. In terms of the clock, really comes down to how do you design a quantum system that give you a very long quantum coherence? How do you push the measurement precision by putting many, many quantum particles together and reach the so-called standard quantum limit? But I think I argue now, it's really time when you can start to build many body quantum states, which is a connection to condensed matter physics. And you start to use quantum optimization and entanglement. And towards the end of my talk, I will show you some quantum entanglement enhanced clocks that start to show real enhancement in the state-of-the-art clocks. And because of this, you know, over the past 2 or 3 decades, what our field is moving really fast. Quantum control has given rise to very high quality factor optical transitions that you can actually investigate. New laser technology is now providing optical coherence time approaching a minute. Sitting in front of the laser pioneers like Ron, it's actually very proud to kind of give you a term report. This coherence time is amazing when dating back to when the laser was first invented. Early pioneers always thought of these lasers as a coherence as good as microwave, and we are finally reaching that level. Frequency combs allow you to basically synthesize electromagnetic fields, and the quantum gas experiments allow you to explore these many body states of atoms. And just as a quick summary of the clock performance, the accuracy, as Hartmut talked about, accuracy is now at 10 to the 1 part 10 to the 18. Measurement precision is below that. But this field over the past 2 or 3 years during the pandemic actually has not stopped. We are now showing the clock measurement precision approaching below 10 to minus 20. Accuracy is being evaluated, and I think it's going to approach mid 10 to minus 19. So as you can see, the systems continue to improve based on these quantum resources. And if we think about clock, the first thing maybe give it to you for many of you who are not in the field, to just tell you about time scales that allow us to build such a fantastic measurement device. If you think about an electron cloud moving around nucleus, oscillating back and forth, if you slow down by 10 to the 15 times, because this period is about 1 femtosecond. If you slow down, you can see 1 cycle per second. And that turns out we have a strontium atom that has a quantum superposition time of 120 seconds. So you can already see during 1 lifetime of its coherent superposition, this pendulum will oscillate 10 to the 17 times, right? Because the period is 10 to the minus 15 and the lifetime is 100 seconds. And if you think about on the other extreme scale of the time, that's the age of the universe. That's about 10 to the 18 seconds, 14 billion years. And this, you can immediately see this 120 seconds is actually pretty special because it's actually the geometrical mean between the oscillating period of the quantum pendulum and the age of the universe. Current quantum technology now allow us to be sitting at this midpoint, that we can actually look for 10 to the 17 quantum oscillations, which equivalently speaking, as if I slow down this quantum pendulum to 1 cycle per second, it would have been oscillating during the entire age of the universe without stopping. But of course, to be able to read out, this is a macroscopic picture of electrons moving around nucleus, and we need a light to communicate with the atom. So you needed this little cheesy animation showing this white sinusoidal oscillation is our phase coherent laser light to be able to tune onto the atomic resonance. And that's the information we're going to gain out of how fast electrons are moving around the nucleus to build this as a clock. So obviously we needed to build very stable lasers, right? To be able to take advantage of such a high quality factor. And indeed, some new latest technology where we're using silicon crystal just happens to have extremely high mechanical quality factor. Dissipation equals to fluctuation. So if the dissipation is less, fluctuation is less. Has very strong Young's modulus, so it's a very stiff against the vibration noise. You can tune to a 0 thermal expansion coefficient by going to some cryogenic temperature like 124 Kelvin. And if you build a couple of systems like this, you can actually bring them together and do a so-called beat, optical beat. These are optical waves oscillating 10 to the 15 cycles per second. If you build 2 similar lasers, bring them together, just like you hear a music fork beating against each other, you can actually hear the beat. And this is the optical beats showing a line width of just a few millihertz or so at a 1.5 micron. And this is telling you this quality factor indeed is approaching 10 to the 17. If there are questions, please making sure that you can just raise your hand and I will be happy to stop and entertain. If you translate this to coherence length, if you had a laser like that, you should be able to move back and forth between Earth and the Moon 100 times and it will still maintain phase coherence if you can solve the perturbation of the atmosphere. And in the end, we are working on a laser that can approaching coherence time of a few minutes. And it would be nice to say the coherence length of our laser is 1 astronomical unit, the distance between Earth and the Sun. And with the frequency comb technology, you can build one stable laser. That stable laser's frequency and the phase information can be distributed everywhere you want it, in the visible spectrum, in the middle IR, even to the extreme ultraviolet. Well, then with such a stable laser, then we want to work on atoms. Of course, in the 80s, when some laser spectroscopy experiments were going on at Stanford, at Berkeley, at the early days, people were using hot cells like this. And if you think about Einstein's relativity theory, time is all relative. If you have a moving clock, we all know, with respect to the stationary observer, the moving clock is going to move slower. And if you have a different gravitational potential difference, the clock is going to move slower and faster depending on the position with respect to gravitational potential. So if you have a system like a hot cell like this, each one of the atom is your little atomic clock, but they're all moving with different speed. And that's actually was a strong motivation where the laser cooling started. And the idea being, instead of having these atoms moving around in a hot cell, well, let's slow them down. And this is actually terribly efficient technique where you send in 3 pairs of laser beams from 3 orthogonal directions in a millisecond. You can cool them from thousands of Kelvin down to millikelvin or even go to a microkelvin. And you can, if you are curious about this, of course, you can walk into a number of Berkeley labs right on campus and watch these laser cooling in action. But just cooling them down is not enough. You have to hold them because even if the atoms are moving very slowly, if you let them go, they're going to fall under gravity. And so there's another really quite long-standing idea is you can form an optical tweezer. And in this particular rendition, it's a single laser beam getting propagated and reflected by a mirror, forming a standing wave. And you have antinodes and nodes. The atoms can be attracted to antinodes if the frequency is tuned right. So you can have atoms, it forms like little pancake, a stack of pancakes. Each pancake can hold tens or hundreds of atoms. And these are the atoms you can use to do spectroscopy. One key idea out of this optical trapping was, well, on one hand, we want to keep those atoms motionally frozen by cooling them down and keep them in harmonic trap formed by light. On the other hand, when I do precision spectroscopy, I'm measuring energy difference between 2 clock states. I want to make sure these optical trapping is not causing perturbation to the energy level measurement I'm doing. Otherwise, your clock won't be accurate. So you have to create a particular wavelength of the trapping where the ground state and the upper metastable clock state experience the exactly same AC stock shift, such that when atoms are moving around in the spatially inhomogeneous AC stock shift, the internal ground and excited state does not experience differential AC stock shift. And that's actually a key concept. The motional degrees of freedom and the internal degrees of freedom are separated due to the fact that you can have this so-called magic wavelength trapping. So once you can do that, you can learn a bunch of these ideas from trapped ions. Hutmer has all the trapped ion tricks, and neutral atom once you can separate the internal and external degrees of freedom, you can do the same thing. You're driving the transition from ground to excited state, but at the same time, the motional degrees of freedom due to the laser cooling are quantized in these harmonic traps. And because the trapping potential looks the same for the 2 internal states, you can drive these transitions as if motional and internal degrees of freedom spin on orbital degrees of freedom are decoupled. And this is a spectrum that we typically observe. You can see that in the middle, it's very narrow. It's actually clock, so-called a carrier transition, where driving the transition without changing the motional degrees of freedom. You can zoom in and you can see fantastic Radi line shape, almost like a classic textbook. And in fact, we can get this line shape much narrower than a few hertz now. You can go down to like 100 millihertz. And then you'll see sidebands. This upper sideband is when you're putting a quanta of the n beta n equals +1. You're putting quanta into the system. Or you could take a motional quanta away, the so-called the red sideband. You can see the red sideband is much more suppressed than the blue sideband. It's because of you have cooled these atoms into the quantum mechanical ground state, and there's no states below the quantum mechanical ground state and motional degrees of freedom. and that's why they're suppressed. There's little hairy lines separation due to one photon recoil is due to the fact that those traps are not exactly harmonic because they're made by the cosine square term. So you have these little photon recoil, but we can cool them down to like tens of nanokelvin, and these single photon recoil energy can be clearly resolved there. I'm sorry. How the red sideband is cold? Yeah, so the cooling is down by the laser cooling that we have, and you cool them to extremely low temperature, much lower than the energy separation of these harmonic oscillations. And that's why the red, you can also do sideband cooling. You can actually drive transitions on the red sideband to take the energy away. But here we don't actually have to do that. It's already cold. Thanks. So a setup like this allows us to do, you can think of where did the Doppler effect go? Doppler effect should become quantized and reflected in the blue and the red sideband. Those are actually Doppler effects, but they are no longer separate. They are no longer affecting the carrier. So you're Doppler free, you're recoil free because atoms are very tightly confined to those traps. There's no photon recoil. The trap AC stark shift differential effect is 0. And so you can then by putting lots of atoms in there, precision improves by square root of n. But as we continue to advance on the clock precision, a new problems appears. And this is, for example, a spin model that appeared in our clock experiments where you have bunch of atoms here. If I zoom out the central pancake, let's say we have a half dozen or dozen atoms in this, and you're doing Ramsey spectroscopy. In the transverse direction, you still have some motional quanta. They're not cooled down to the ground state. The ground state is only for the longitudinal direction. When you do clock experiment, you're doing nothing but using a laser field to rotate on the so-called Bloch sphere, which is representing the two spin, pseudo spin app, pointing down, pointing up. Those are two atomic states. And of course, Bloch sphere means you can create arbitrary coherent superposition of ground and excited state. That's the spin path. And people call it qubit. If you want to call it qubit, you can call it qubit. And as you drive these atoms into a coherent superposition, and we use these atoms to be fermions. And the fermions have this anti-symmetrization postulate because they have a Pauli exclusion principle, meaning if you have two fermions and you write down their wave functions with respect to exchange of the position, the wave function has to be anti-symmetrized. So if I use ground excited state to represent the spin degrees of freedom, N1, N2 represents the motional degrees of freedom in the transverse direction. The overall wave function has to be anti-symmetrized if I drive internal states in a symmetrical way. And this negative sign is what people call the P wave interactions in the lowest order when the temperature is very low. And it turns out in such a two-dimensional trap, the P wave interaction is not very sensitive to the actual motional quantum number n. So you can actually take all these atoms as if they have a collective interaction. You can actually think of the spin as nothing but n times 1/2. And n, so total spin is n/2. And through the collective interactions, you can actually write down a Hamiltonian that looks like SZ, the Z component projection squared with a coefficient in front of it. And this coefficient, if you wait for the atoms to interact with each other, it actually shears the quantum mechanical noise, which previously this little fuzzy ball indicates quantum mechanical noise, right? Indicates uncertainty principle when you have this coherence of position and you make a projective measurement, you don't know whether it's pointing down or pointing up. That's the quantum noise. And this quantum noise due to this collective P wave interaction, can actually be distorted like this, creating a classical or a non-classical spin noise distribution. And you can actually do spin squeezing experiment if you have heard of spin squeezing. And I'm going to come back to the spin squeezing because that gives you entanglement to enhance the measurement precision. In the end, when we do spin squeezing, we do not use this particular technique because there's actually loss term associated with it. And so we don't use it, we use cavity QED, but this is the basic idea. You can make these individual spin noise to become correlated such that you can only get one copy of spin noise instead of multiple copies. So because of these interactions, a few years ago, we thought, well, maybe we should restrict the transverse oscillation motional degrees of freedom as well. Let's create, instead of a one-dimensional optical lattice, let's create a three-dimensional optical lattice. And if the temperature is really low, the Pauli exclusion principle will guarantee one atom per site. And you will have no more interaction, right, in the system like this. And so now you can think about scaling up the system, building a large quantum system where you can have 1 million atoms in there. If a coherence time is 120 seconds, then you can imagine you can build a clock with only 1 second averaging time. The clock measurement precision will be at the few parts 10 to the minus 20. This number is actually, when we were just estimating this kind of a stability, we were very much encouraged, because if you get to this level of clock stability, that means you can use atomic clock to directly sample gravitational wave. You know, in LIGO, when people measure the LIGO gravitational wave, remember the strain they measured is 10 to the minus 21, 10 to the minus 22. That's when the gravitational wave is stretching the two interferometer arm in differential way. But of course, gravitational wave is going to have an impact on time too. And you can compare two different clocks and see if the gravitational wave comes, whether the time is changing at this. If I average for 100 seconds, this will have a precision of 4 times 10 to the minus 21. So it's getting close to that level. And this was proposal back in 2016 or so, and we demonstrated this clock at that time. But now we actually, over the past 5 years or so, we did push the record of precision to, at the time was few parts 10 to the 16, and we improved it by a factor of 100. And I do think in the next decade, probably we'll get to that level, and we'll come back to that. It's actually quite exciting to see gravity, quantum physics start to play a role. Not a quantum gravity, but nevertheless weak gravity. You can start to see how that affects the many body quantum physics. But our field. Oh yeah, sorry. Is it? Yes, it's a large number of atoms helps to improve the precision. And the hope is also using entanglement, maybe even 1,000 atoms to make entanglement. It will make that kind of improvement. Thank you. And another thing, I'm actually very happy to say that the field of atomic and molecular optical physics is a very collaborative field. People support each other, and ideas freely flow with each other. And that's why the field is moving so fast. There are 2 young faculty members, Manuel Andres at Caltech, Adam Kaufman at Jilla. You know, they heard about this 3-dimensional crystal idea, and they say, well, we can actually do this with optical tweezer. And this is the experiment done in Adam Kaufman's lab. And you can see they start to have individual addressability of individual strontium atoms. And they can actually do quantum entanglement in Bell states, GHZ, and so on. So you start to see a new platform emerge that it was optical tweezer. And that's a really interesting platform where you can sort of the boundary between building quantum computer and a quantum sensor is blurred. So I mentioned about quantization of the motional degrees of freedom. Here I'm showing you a picture of quantized interaction. I mentioned that atoms can interact. Even with fermions, they can interact with the P wave. But now imagine you create a lattice like this. You're putting them into the 3-dimensional crystal, and you can see the 3 set of sidebands. Remember that you were asking about the red sideband cool down to, because these atoms are in the motional ground state, there's no red sideband whatsoever. It's only blue sideband. There's 3 set of sidebands because there are 3 different directions, X, Y, Z. And now what if these are identical fermions, so only when the sufficient low temperature, they're all occupying the lowest band. You have 1 atom per site. Strontium-87, this fermionic isotope, turns out it's got 10 different nuclear spin states. And these 10 different nuclear spin states in principle can contribute so-called hyperfine interactions. But because the clock states I'm investigating has total electronic angular momentum J equal to 0, so I thought J equals to 0. So even though you have 10 different nuclear spin states, you can make different colors of them just to label them, but they do not contribute to the electronic interaction. They just label themselves. That in the sense that if I have spin impurity, if I have different nuclear spins, they will be able to occupy the same site because no Pauli exclusion principle will prevent them from doing this. But they will have interactions when the 2 atoms are sitting on top of each other. And we can very nicely resolve those. If imagine you have 2 atoms occupying the same site, well, you have two sidebands appearing. One is a positive, one is a negative. And you will be wondering why only 2 sidebands? Because you have 10 different colors. What turns out, you can pick any pair of color and the interaction is all equal. It's called SUN symmetry. And not only this, we can actually put more, we can pile up 2, 3, 4, 5 atoms on the same site. And you always have 2 pairs. When you have 2 atoms, 3 atoms, 4 atoms, they're always paired up. And that's because there's only 2 symmetrization you can have. Either nuclear spins anti-symmetrized or nuclear spins symmetrized, and vice versa on electronic freedom. And this shows very nice, this SUN, so-called SUN symmetry groups that was initially proposed for high energy physics and particle physics. And this is the Berkeley slide. I think Berkeley people love to take images. And I started with Yale student, Ed Marty, when he came to Jela as a postdoc, he really emphasized, we got to take pictures on everything, high resolution images. And that we just tremendously benefited from Ed's foresight. And in this picture, for example, recently we were able to create a so-called 3-dimensional band insulator. Before there's a picture of every atom occupies one side. How do we prove that? Well, you can take a picture, and as you put more and more atoms in there, you can see in the center, every side is filled with one atom. So that's the filling is 1, and it's plateaued. You can no longer add more. If you add more atom, they have to go to the outside, unless you add so much more that eventually you're going to go have to higher band. So this is interesting that you can directly observe this kind of a band insulator structure. Ed led this experiment. He said you can apply a magnetic field gradient, or for that matter, any gradient, whether it's a gravitational gradient or magnetic field gradient, and you should be able to do high precision spectroscopy with a high spatial resolution. So combining spectroscopy resolution and a spatial resolution all together, and you can freeze the quantum coherence of the atom regulated by the magnetic field onto this picture that you take. And you can actually use this to measure field gradient to very high precision. And later on, we're going to use this to measure gravitational field gradient and gravitational potential. The most recent work, actually, Ross Hudson, he was an undergraduate student here from Berkeley, from Putnam's group, was able to drive these atoms by putting them in coherent superposition. And remember, these clock states are extremely long-lived. The lifetime is 120 seconds, indicating the dipole moment is extremely weak. The dipole moment is actually 1 micro debye compared to 1 debye of dipole moment. So here you can actually study dipole-dipole physics. When this light is propagating into this 3-dimensional crystal, you're driving every atom into coherent superposition like a radiating dipole, except those dipoles are 10 to minus 12 orders of magnitude smaller than the regular dipole-dipole interaction. And nevertheless, if you have the patience to wait for the coherence time of a few seconds, you can see, you can actually take a spatial image, a map along the clock where some dipoles in the middle get more clock frequency shift versus atoms which are not. So you can start to see collective dipolar interactions and take an image of those. And at the level of 10 to minus 19, 10 to minus 20 level. It's like a phased array of long range radio telescopes where each one of them is phase coherently connected, except these dipoles, of course, are quantum mechanical, and you can flip one of them and have a phase transition. So now let me switch a little bit towards the clock comparison. Why clocks? Why we are building clocks, right? How do we compare clocks? There's 2 ways to compare clock. One is to have 2 different atomic systems that drive with a common oscillator. That way you can remove the clock, the oscillator noise. You're just comparing the 2 quantum systems directly. The laser is like a little bridge, but the common noise can be removed. But you don't always have this capability. The other way is to have a separate local oscillators. And what you are going to do is a measure of frequency ratio. So I'm going to tell you both of this a little bit, maybe frequency ratio first. And in the frequency ratio measurement, this was the experiment we did quite a while ago. Victor Flambaum, remember, he was visiting from Australia, and he said, one thing you can use a clock to test is the local Lorentz invariance. How do you know, at a different gravitational potential, the physical constants like Fine structure constant is the same? this testing the universal fall, fundamental constants versus gravitational potential. So we did actually the first international comparison. This is actually the first international comparison of any optical clocks at the time. To do that comparison, what you're measuring is essentially in Boulder, Colorado versus Paris versus Tokyo, you're measuring the ratio of a strontium frequency against cesium frequency. Cesium is a standards of time, is SI unit of time, second defined by cesium. And the cesium has all the GPS connection, so we can make a cross-continental comparisons between the cesium clocks. Strontium at the time cannot make those cross-continental connections, so you can make a ratio, strontium with cesium, and compare them and plotting them on top of each other. And here shows sort of a sinusoidal oscillation as the annual rate of the Earth moving around the sun, where the gravitational potential is changing by 5%. And see if you can observe any coupling of the gravitational potential to fundamental constants. At the time, this experiment sets a limit on both the linear drift or sinusoidal oscillations of these fundamental constants as a function of the gravitational potential. These days, this has been pushed down to now 10 to the -17, especially with the trapped ion experiment in PTB at Germany. But we will continue to push on these clock comparisons. The most recent clock comparisons are done in Gela versus NIST. This is 1 mile apart, 2 kilometers apart between NIST and Gela. And we have two different ways by using fiber to connect the two campus. But the latest technique is actually by shooting lasers directly between the two buildings. We actually have a fiber connecting from our lab in the basement all the way to the top 11th floor, and then use telescope shoot a laser beam across the city of Boulder and received by the NIST campus. Of course, the laser phase noise is canceled by shooting laser beams across each other and measuring the laser phase noise through the perturbating air. By canceling this laser noise, we can compare both the fiber loop and the open air loop, and comparing comparison clocks at the level of 10 to the -18. Here shows the ytterbium clock on this campus versus strontium clock, and it's showing averaging down to just low past 10 to 18. And you may ask, why do you need, if you have a fiber connection, why do you want to do this air connection? Well, that's because in the future, we want to compare clocks safe at UC Berkeley against Boulder. How do you compare that? That's too expensive to lay down a fiber. Would have been easy if there's a satellite that can see both Boulder and Berkeley, and it's just using the laser beams going up and down. So this laser light is already covering about 2 kilometers. If you can extend this to 10 kilometers, you will clear the atmosphere. You will be in the space already with satellites. So this technology is going to come. This would become the air space connection for optical clocks to make a clock network. And as I said, why this is important is obvious. You want to have all these optical clocks to be able to compare it against each other directly instead of through cesium clock, because cesium clock precision is 1,000 times worse than optical clock. So in order to compare to the optical clock accuracy, using cesium would take way too long to average it down. And the time is actually now the only unit has not been redefined recently. Every other single unit, 6 units have been redefined based on quantum phenomena. And so this is going to come in the next 5-10 years to be redefined based on not on cesium anymore, but on one of those optical transitions. But obviously, it's clocks are important for industry, for communication, networking, and the fundamental science. But another interesting area of using clock, since you're already doing comparisons, you can compare clocks of different atomic species, and they have, depending on the transitions you use, whether it's in molecules, in atoms, or even in nuclear transition eventually, they have a different dependence on the fundamental constants of alpha. By comparing them and looking for possible variations of fundamental constants, you can actually put some limit on the ultralight dark matter as example. And that's because the fundamental constants alpha, the fine structure constant, can be reflected in the frequency. If alpha is changing, the transition frequency will change, fractionally speaking, and with a different k scaling factors for different atomic species. So you can, by comparing different atomic species, you can put a limit on the alpha is varying or not. And this ratio of frequency measurements from different clocks will allow you to be sensitive to the variation of alpha. And using techniques like I mentioned, this border area network of clock comparison, we are already putting some of the lowest bound of the possible extra light dark matter connection, coupling strengths to the ordinary matter and ordinary field. And as you can see, it's setting the lower bound, as well as the strontium clock comparing against the silicon cavity itself. So this is an interesting connection to fundamental physics, such as dark matter search. Now, talking about clock comparison within itself, I'm going to give you the final experiment that we are doing. Our traditional clock was made of this kind of an optical lattice, as I was explaining, and you can think of each atom is confined in very deep lattice, and they have no, don't jump over each other. The lattice is sufficiently deep, unless we want to actually study quantum matter, like band insulator and so on. We will purposely tune this down and looking at the interplay between tunneling and the on-site interactions and quantum statistics. But traditionally, we have very high, very deep lattice like this. But what if you start to tune down the lattice depth, and tune down to such level where we actually build a lattice supported by cavities? This reminds you of some of the experiments going on in Holger Miller's lab, with an optical cavity to clean up the wavefront, creating a scanning wave, and you can have these atoms confining there. And you can really, by leveling this really well, you can go down to very, very shallow lattice, like a 3E recoil. And as for some of you who are not in atomic physics, you have to excuse me or using this kind of funny unit to tell you about the depth of the confinement, except you can think of this, each photon has a recoil energy when they hit atoms. And these are just the 3 or 10 recoil units of the photon that we are using to confine these atoms in the lattice. And this lattice is now so shallow, 10 times shallower than what we traditionally use in clocks. And this experiment is actually brand new. This was the experiment we decided to rebuild when the pandemic started. We couldn't no longer compare clocks. We said we're going to compare clocks within ourselves, and we started to build this extremely low, shallow lattice in 2020. And this was something really interesting, because when you go to such a shallow lattice, the quantum mechanical wave function spreads out. It's no longer confined in a single Wannier orbital. Rather, you have to use so-called Wannier stock states to describe it. And this is the kind of a coherent amplitude of the quantum mechanical wave function for the atom, which was located here before, but now it's spread out to neighboring sites. But of course, remember I mentioned that we have this magical wavelengths, the ground state, electronically excited state, and they share the same trapping potential. And you can drive this with lasers. They can drive on the same site. But because the wave function is spreading out on several sites, you can drive off-site. You can create a weird coherent superposition where on one site, the atom's in the ground state. 10 microns away, this atom is in the same atom, of course, is in coherent superposition in the excited state, but 10 microns away. Some things like that. How long can the coherence be? Well, actually, this is actually experimental data. It's not a theory plots, and it's showing individual lines of how we're driving it. And you can see the spacing between this central line is on-site interaction, on-site driving, sorry. And you can see the sideband, which is spaced apart by MGH. H is lambda over 2 just because each side is the distance between each side, vertical distance is lambda over 2, half wavelength. And so this is like high school physics. The gravitational energy has a difference of MGH, right? And that's why you can use this sidebands directly measure your local G. Just telling you the gravitational potential difference between the neighboring sites. This is something we learned from condensed matter physicists, of course, Wannier stock states that we learned. And each line is extremely narrow, indicating very long coherence time. How narrow is it? Well, we can actually do this imaging spectroscopy that Ed Marty helped us to build. So you can, this atomic cloud, about 1 millimeter long, we can separate into 2 regions and take an image of those. And it's like comparing a bunch of quantum pendulum in this region versus the quantum pendulum in this region. And just this afternoon, a postdoc in Holger Miller's lab was telling me about, ellipse. And I'm just going to show you the same ellipse because you can look at the evolution of atoms in the upper region versus evolution of atoms in the lower region. If you prepare them in coherent superposition, you wait 30 seconds, half a minute later, you can still see these 2 quantum pendulums are oscillating in, more or less in phase. It's actually slightly becoming out of phase because there's a little ellipse developing. If they are truly in phase, it would be a single line. But you can clearly see it's still coherent. Even after 50 seconds, it's still coherent. This is showing you this long quantum coherence in optical superposition that's existent in these shallow lattice. And this shallow lattice, without the shallow lattice, we wouldn't be able to do this because the lattice actually scatters photons. So if you go to deep lattice, we would not be able to enjoy this long coherence time. So now there's an interesting interaction. I remember I showed you in the long time ago, a single pancake where atoms are interacting, they're causing like spin noise become correlated. And that was due to the so-called P-wave interaction. Now imagine that I have a stack of pancakes like this. Within each pancake, atoms are interacting with the P-wave. But because the quantum mechanical wave function extends over neighboring sites, the neighboring sites, these atoms are distinguishable from this site because the laser wavelength that's propagating along the lattice spacing is different with respect to the wavelength, the lattice spacing constant. So you have an S-wave, P-wave interaction. These are distinguishable fermions between neighboring sites. They can start to interact. And by adjusting the lattice trapping depth, you can actually tune the balance between the S-wave interaction, the P-wave interaction, such that the interaction effect on the clock shifts can be tuned down to like 10 to the minus 21, completely null the wave. And this, again, maybe, even if you do not understand completely the macroscopic picture of this tuning, well, one thing maybe comes to your mind is you have Hamiltonian. Now you can actually tune it in the lab and do whatever you want to do. You can use this to simulate quantum mechanical spin models, or you can tune it to make sure the interaction is no longer manifest in your clock. And this modern AMO lab is all about being able to control quantum system. This is one example. By tuning the lattice depth, which is essentially you can think of how much quantum mechanical wave functions spread out between neighboring sites. By just the field of light, by tuning down the intensity of the laser. And so this is actually the intensity of the laser on this axis. And as you tune this, you can see this interaction is here, it's P wave dominated. This is the S wave dominated, and in the middle is 0. And so with those, once you have tuned up all this, you can actually now, this comparison is no longer about gravitational potential energy, but rather it's actually a real GR effect, the so-called gravitational redshift. You compare the top half of the clock versus the bottom half of the clock, and just compare them to see what clock is running faster or slower based on their distance to gravity. And you can see this coming down very nicely, reaching 10 to the minus 20 in about 10 to the 5 seconds. And the gravitational redshift is 10 to the minus 20 with the 100 micron. And as you get closer to the Earth, the center of the Earth, the time slows down, right, because of gravity, right? This is gravitational redshift. And indeed, we can measure this. Similar work you probably have heard from Shimon Kokowitz, who I think visited you maybe in the spring and told you similar things. Their work in that time when we published the paper side by side, they did not measure the gravitational redshift. But since then, they have done the follow-up measurement to show this gravitational shift measurement at a millimeter scale. Well, actually, uncertainty is really at a 200 micron scale that we can measure. The point here was not to test redshift, but rather to show that you have this technological capabilities to be able to see time dilations at such a small scale. And why is that interesting? Well, think about into the future when this kind of a picture where the time is really soft. What if we get to this an interesting scenario. If I have an atom absorb the photon, this atom goes from ground state to the excited state. But because you absorb the photon energy, these two levels actually have different mass. The ground state is the original mass of the atom. The excited state, you have to take into account the photon energy is being absorbed in there. There's h nu of a c squared term that adds to the mass. That term is 10 to minus 22. This photon energy induced the mass. It changes the mass by 10 to minus 22. But actually, by incorporating this effect into your single particle Hamiltonian, you can actually explain both the time dilation effect due to the gravity, as well as due to the motion of the group of freedom. So now this is the interesting area, and I'm sorry to have some mathematical expression here. I'm not meaning to explain to go through the symbol, but just want to give you this impression. You have this quantum particle physics, like a spin model in condensed matter physics. And you have these Hamiltonians, which write on interactions on site versus interaction off site. This S indicates the total spin that I was explaining earlier. And what's the really interesting aspect is now you have to add this GR term. Every single layer has slight different gravitational redshift, right? And this term has always been there. It's just previously we do not have the precision to see it. And so if you put this GR term in, when you look at the on-site Hamiltonian part, that part is going to commute with GR. But the off-site part does not commute with GR. But the atom interaction between different layers actually have a different time. And so you can use this to actually look at how the many-body physics or entanglement will be modified by the gravitational redshift. And that effect is on the order of 10 to minus 23, 10 to minus 24. We are not quite there yet. This is actually even more demanding than to see gravitational wave. But 2 orders of magnitude away, being able to start to see where quantum mechanical wave function over one single quantum mechanical wave function, the time starts to be different and will have a real impact on the dynamics of the many-body physics. I think this is to me personally speaking, this is a very interesting area. Again, it's not a quantum gravity, but it is speaking about the connection between very macroscopic theory of general relativity and a very microscopic theory of quantum mechanics. And we just don't think about this, right? At 10 to minus 23, you will feel like such a small scale, who would be able to measure it? But in the past 10 years, the progress has been this fast to make you think maybe in 10 years this is possible, or maybe it will take another 50 years, but who knows? We just have to push on this. So with that, in order to really do this measurement, you really need to understand the quantum noise really well. You were asking me, is it because you use lots of atoms? The answer is partly true, but hopefully in the next phase, we will actually use quantum entanglement to allow us to go further. If you think about where the quantum noise is, remember you put atom in coherent superposition, you have this phase factor. This phase factor is what we are reading out as a clock, energy difference times time t. And when you read them out, there's a fuzziness of the quantum noise because you do not know a priori whether it's spin up or spin down. And that's the quantum noise aspect. So therefore, the typical standard quantum limit is of many particles is 1 over square root of n being the particle number. But what if you create entanglement? What if you create, I always think of entanglement as nothing but atoms start to conceal each other's noise because there's only one copy of noise left if they're entangled. And that means instead of n copies of a noise, you have only one copy of noise, but you still have n copy of signal. So signal to noise ratio goes as 1 over n instead of 1 over square root of n. That's a big gain if you can do it. But entanglement is very difficult. If you can do that, of course, you can build that. All the quantum information science is based on whether we can take advantage of this. And actually, we have another very, very recent experiment was also built during the pandemic in 2020. Is doing the spin squeezing experiment. There are lots of pioneers like Eugene Polzik, Vladan Vuletic, Mark Kasvich in the neighborhood here, in Stanford, James Thompson, and so on, have pushed on spin entanglement, spin squeezing experiments. And what we are doing is using a cavity QED. This is something when Dan and I were both at Caltech learning from Jeff Kimball. And we built this experiment where we have this cavity system, very high finesse cavity, and we can build this lattice as if it's an elevator. We can put atoms into these pancakes, and those pancakes can be moved up and down. And this can just be done by running the laser wave, slightly different phase, and it can move these pancakes up and down. So we can put a sample A inside, get a spin squeeze, and then move it out and put a sample B in there. And this allows us to not only demonstrate spin squeezing, but directly compare clocks. You have two spin squeeze clocks, and you do direct comparison without subtracting any noise. We want to show there's a quantum advantage. And I want to call out to this guy, Jeff Kimball. We learned a lot of optical cavity QED from him. This was his, I think, 70th birthday, I think, or 65th birthday, sorry. But you can see a lot of people showed up, and Dan is somewhere. Dan is here. And it was just great, learning these kind of optical cavity QED technologies, and now we can use this. And so, as I mentioned, we can do these two elevator kind of a way, put a red sample in there, get a spin squeeze, get a blue sample in there, get a spin squeeze, and then compare these two clocks. And indeed, this green curve shows the quantum projection noise limit, and we are 2 dB below this. It's a very minor, maybe very humble beginning of a quantum entanglement start to help you in terms of their measurement. But I'm very proud to say, though, this averaging is going down to 10 to the minus 17th. So this is no longer just a demonstration experiment. Make everything working at 10 to the minus 11, and I show you a 3 dB improvement. This is, in some sense, it's a state of the art. The best ion clock is actually 10 to the minus 15. So we are really showing this entanglement can help in some of the operational clocks. It's not quite the state of the art that I told you about, measuring gravitational potential at a few hundred microns. But nevertheless, this is just the beginning where the quantum entanglement is showing some promise. So maybe this is my end of my talk, is to share with all my Berkeley friends and the students and the postdocs that, build tools like this. Of course, you can feel it's like building a telescope, looking into the deep universe of the fundamental natures of our universe. And there's discoveries to be made, dark matter, gravitational waves. But you can also build a tool that's going to help out our environment, because it also becomes a microscope. You can actually do all the Earth geodesy with clocks, where you can actually measure how the groundwater is migrating, how the glacier is melting, things like that. And with that, I want to also thank many of the students and postdocs in the group, and long-standing collaborators with Anna Maria Ray on theory side, but a lot of experimental groups in JELA, as well as many friends in PTB that we co-developed the silicon cavity from Germany, and NIST colleagues. Thank you very much. Yeah. Okay. Yeah. Sorry, so essentially the idea is the following. Maybe it will take too long to go back there. The idea is the following. You have atoms you trapped in the lattice. You shine the clock laser, you put them in coherent superposition. And normally the Ramsey experiment would go, you wait for a while until the system is evolving, and you probe again, right? And that's your Ramsey experiment. And so as you probe again, you can use the image to read out whether the state is in the excited state or the ground state. You can shine the light, which as the final state readout, you can shine fluorescence light onto those atoms and just read the fluorescence from how many atoms are still remaining in the excited state, how many atoms in the ground state. And that's how we are averaging away the quantum noise. But there's two different crowds. Because they're being driven by the common laser. And so you can compare this image, how many atoms are left in the excited state with how many atoms are left in the excited state here, and just compare them frame by frame by frame, and you can build up the correlation between those. Oh, it's just a CCD camera. Yeah, just CCD camera with decent enough high resolution, spatial resolution, a few microns. Some of the best resolution we have is 1 micron. Some quantum gas experiments can go down to half a micron where you can see individual atoms. We do not see individual atoms. We see collection of atoms. But it's a pretty high resolution imaging just looking at the fluorescence. Thank you. Yeah. Yeah, no, this is exactly right. This is actually exactly the Ross experiment is going. When I was just telling you that when we drive these dipoles, which are relatively weak, but if this had been strong, you would be talking about super radiance and so on. But actually, there is a super radiance. Those very weak dipoles, when they start to collectively interacting with each other, they have a 1/r interaction because it's the e to the ikr over kr. It's a retarded potential. So it's a fairly long range. And you get all these atoms interacting. Actually, depending on which angle you're going in, you can actually have a Farag angle or not a Farag angle. And in some sense, you're looking at a collective dipole-dipole interaction both in the entire complex quadrature, whether it's the real part or the imaginary part. The real part is a phase shift. The imaginary part is a super radiance. And it's just those dipoles are so feeble, and you need a clock experiments to see this kind of interesting dipole-dipole interaction. But it's close to what Bob Dickey's original picture, individual quantum absorbers are sitting in a very ordered spatial pattern, and you go in with some excitations and see how they are exciting each other. It's like what's beautiful about those experiments is like very textbook kind of thought experiment, but now you can actually realize them as you move along with such high precision. Does that make sense? It's connected very much to like what Derek Chan want to do, what Jeff Kimball want to do, the dipole-dipole interaction. Maybe Dan was thinking about these kind of experiments as well. Yeah, okay, imaging is the same thing as the previous question. So once we see them, you just wait, you turn on the coherence, you wait for 10 seconds, and they will evolve according to whether some atoms in the excited state, some atom in the ground state. And you can just excite them with a fluorescence light to see which atom are in the excited state, and you can read that out. You can do both absorption imaging or fluorescence imaging. Okay. Yes, the deep lattice, it turns out what was limiting our coherence at the time was that with the deep lattice, there's a photon scattering. And the photon scattering really is because of the triple P0 state can Raman scatter photons go to excited state and decay back down. And that will destroy the coherence. You have a ground state. The ground state is actually very safe, but the excited state, it's still close enough to some other more excited states, and they can do Raman scattering. And that Raman scattering was limiting our coherence time to 20 seconds or so. So I made a little joke saying, oh, we cannot compare to other people, therefore we compare ourselves. But it was actually motivated by the fact that we were limited by the photon scattering at 20 seconds. So we want to go to very shallow. But as you go to very shallow, the first thing that comes to your mind is whether you can still have coherence surviving. Wannier-Stuck state turned out to be perfect, and Rachel, thinking back, it's very natural to think, it's a coherent superposition of individual Wannier orbitals, and they should be coherent as long as you're not having the potential. If you turn down to like a 1 recoil, we start to see atom become lost, and they start to file away, and then you lose coherence. So in many ways, it's like similar to your motivation, to keep the atoms there, freeze the coherence in the lattice, and wait as long as possibly can, and then read out. You said pros and cons. It seems like I'm only saying the cons for the deep lattice. And I think that's kind of true because the photon recoil is clearly a problem. And you can go to much longer detuned wavelength, but the problem here is we have to keep the magic wavelength also. And that's really the limitation. So I think I understand the Yes. Yes, yeah. Anti-node, anti-node. It's actually anti-node, yeah. It's because it's anti-node, so the pancake, the atom is attracted to the laser. So they cannot go out because there's a Gaussian beam, the intensity is still the maximum. Yeah. So if it's a node, you won't prevent them from going out. And if it's that people call it blue detuned lattice, in that case, they will avoid the anti-node. And in that case, you have to build a 3D lattice to confine them. That's exactly right, yeah. Maybe one last, or two. The sideband or the tuning? Oh, yes, that's because the polarizability of the light. When you tune it to the red, it tends to AC stock shift to the lower energy. So the atom gets attracted to the light. While you tune the blue, it's exactly opposite. Yeah, it's yeah, so the atoms like will be repelled by the light. But you both are relying on the resonance. It's just like opposite sign as you tune to the different polar, either side of the tuning, it's got opposite sign of the polarizability. One is attractive, one is repulsive. So in order to do 3D, exactly was the question. If you only have one single beam, you'll never be able to trap atoms because if it's a blue detune, you can repel them. But you can do 3D. You can be trapped in this gray area where all the dark spots around you, and you have to be sitting in the interference minimum. And that's possible in 3D, but not possible in 1D. Thank you.